So our last speaker is Christoph from Copenhagen, and his talk is about quantum information bottleneck function.
Okay, thanks a lot. Yeah, I'm going to talk about the quantum information bottleneck function, and in particular, the convexity and operational interpretation of this function. So this talk is more going to be an information theoretic talk, but I'm going to do my best to motivate why this might be interesting also for people working on computing and more like practical applications. So let's start by looking at some fields where in the classical information theory or in classical computing, the information bottleneck turned out to be really useful. And those are in particular things like deep neural networks, video processing, or clustering of information. And what do all of these things have in common? In general, those are problems where we have huge data sets, and we somehow want to process that information towards a certain task. So for example, in a deep neural network, there's lots of data which has some labels, and we want to find an efficient representation of that data towards answering a very specific question. Let's say, what content can we see on a picture or something like that? And the information bottleneck is very intrinsically related to this question of minimizing an amount of data, like compressing data, but keeping the information towards a very specific question. And to have this in a more mathematical terms, what we want to look at is like sufficient statistics. So what a sufficient statistic is, if I have data or some random variable x, and I apply a channel to it, then I want to keep all the information in x concerning a related random variable y. And this I can write mathematically with using the mutual information. So the mutual information between x and y should be the same even after I apply that map to x. That means I preserve all the information x has about y. Now, of course, this is like lots of maps do that, so this is in particular not very useful for machine learning or something. So what we want to look at, what we want to have optimally are like minimal sufficient statistics. A minimal sufficient statistic is a very similar thing. So we have what we had in the first equation is now a condition. So we want to find a map that preserves all the information, but at the same time throws away as much information about x as it can, so gives us a very efficient representation of x. But now, of course, if we look at applications, that's often not possible. Sometimes the question is very complicated or the data set is just too big. So what we look at instead is an approximate version of this problem. So you see this equation looks essentially the same. Just now, the condition in the argument, the condition of the optimization, it's not an equality anymore, but we just require it to preserve a certain amount of information towards answering the question. And this equation on the bottom line, if we want to evaluate it for a certain parameter a, this is exactly what's called the information bottleneck function. And to give you some further motivation, let's briefly look at some classical applications of this. So in particular, the researchers around Tishby, they have used this to investigate deep neural networks. And as you can see from the title, opening the black box of deep neural networks, their goal was really to understand why does a neural network work in the first place. And how do we think about this? So if I look at a deep neural network, I can see on the left I always have, I guess all of you have seen a picture like this before. On the left I always have like an input layer where I put like my data set x, and then I process it through many hidden layers, let's call them T, and on the right side I have an output layer which should answer my question which I want to figure out. And now I can understand everything that happens before a fixed layer T as an encoding of my information, and everything that happens after that layer as a decoding. And of course, now I can assign like mutual informations between a fixed layer and the data, and also between the layer and the answer. And those information quantities I can look at and try to draw conclusions from them. one very simple conclusion I've put here on the bottom. So from information theory, we have something that's called data processing. And that tells us that through the layers, the information has to decrease. In particular, the information about the data. So they make figures like these, where you can plot all the different layers of a neural network. And now, optimally, if you train your neural network, those dots are going to move, and they're going to move to the left upper corner, which is exactly the spot where there's maximal compression, while keeping most of the information we need to answer our question. And one last slide about this. So what they also found for very particular problems is if you plot the optimal information bottleneck curve and you plot the layers of the neural network, you actually get that those are surprisingly close. So for some problems, it seems that deep neural networks really approximate this optimal behavior which we might want to have. And this kind of suggests that we can use the information bottleneck function also as a, as a benchmarking procedure for machine learning applications. But now, of course, mostly I want to talk about quantum. So has this been done in quantum? Previously to our work, there were 2 papers that have discussed the quantum information bottleneck. The first one was the one to introduce the concept to the quantum information theory community. And well, they have lots of interesting stuff, but they look at it in a very specific, towards a very specific problem and not so much in an information theoretic sense. This has then been done in the second paper, where there was the first attempt of providing an operational interpretation of the quantity itself. And they managed to do so up to a conjecture, which is that the information bottleneck function is convex. And now let's look at how does the quantum information bottleneck actually look. And if you look at the formula on the top of the slide, you can see it looks pretty much the same as the classical version, but there are some main differences. So the first thing is, of course, for the mutual information in the argument, we can do exactly what we do in the classical case. We apply a channel to our initial state rho xy. And this gives us a mutual information we can evaluate. But since we're in the quantum setting, we can't copy information. We have to play a trick by purifying the initial data state, let's call it that, rho x, and apply the map to this purification. But this is a bit inconvenient for analytical reasons, because now both mutual informations are evaluated on different states. And this makes it much more complicated to handle this quantity, and I get back to that on the next slide. The second difference you might notice is that the optimization is now an infimum instead of a minimum. And this is simply because in the classical case, we know a bound on the dimension of W needed in order to achieve the optimal value, while there's no such bound in the quantum setting. And this is a problem, in the quantum information community that is very well known and appears, for example, also for squashed entanglement and other quantities. So let's come to some contributions. So the first thing we prove is that the information bottleneck function is indeed convex, as it was conjectured in the paper by Salek et al. And sometimes these very abstract-looking problems, they have a very simple idea to solve them, or just need a very simple idea. And in fact, here the idea we found is that if you do the purification trick already one step earlier, so you purify your state rho xy, you can actually use very simple arguments to see that there's an isometry relating the state tau, which was annoying us on the previous slide, with the purification of the initial state. And using this, we can evaluate our quantity now in a different state, which is actually the same which we used in the other mutual information quantity. So the advantage of rewriting the formula like this is that we now can evaluate all quantities on the same state, and this makes it much easier to track the quantity analytically. And the rest is really just kind of like a standard procedure using the idea of flag channels to prove the convexity. Now, the second thing we looked at is the operational interpretation. And well, there's some arguments why you could maybe find a nicer one than the one provided in the previous work. And we tried to do that by, again, getting inspiration from the classical setting. So there's a way to relate the classical information bottleneck function with the problem of assisted source coding, which is a very natural operational task. So here you have a joint probability distribution, x, y. Each of them is owned by a party, and they can encode them. And the goal is to, after the procedure, recover the information in y, while x just acts as a helper. That's why it's assisted source coding. And if I now limit the rate at which the helper can send information, it turns out that the optimal achievable rate is related by the equation on the bottom of the slide to the information bottleneck function. And now we do the same thing in the quantum setting. So their assisted source coding was investigated by Hirche and Watanabe. And the picture becomes a bit more complicated, but I think you can still find all the important elements. Just one thing is new, which is now there's some entanglement assistance between the helper and the decoder. So yeah, let me just briefly give you an idea how the proof here works. The converse is basically playing with entropic quantities, so that's maybe not that insightful. But if we look at the achievability part, we extend the decoding map, and we split it in like 3 separate steps. And now we can use very elementary protocols to actually find the achievable rate. And those are the quantum reverse Shannon theorem, aka channel simulation. So we use that to simulate the action of the channel, which is actually the same as in the optimization of the information bottleneck. And this simulates the helper. And then after the helper has done his part of the job, we use a protocol called the fully quantum Slepian-Wolf protocol, or coherent state merging, to order the systems or to bring them in the right place in order to achieve our task. So just puzzling together these elementary protocols, we get the optimal rate for the assisted source coding, which then is related to the information bottleneck, giving an alternative operational interpretation. Okay. And I also want to talk briefly about some numerical results, which are interesting in one sense, that we so here we use an algorithm that was already presented in the paper by Salek et al., but we generalize it in certain ways to allow more parameters. And this comes back to the problem I presented when introducing the formula, which is that we don't actually have a bound on the dimension of the system W, so the output system of the channel. And in this, what you can see is in this numerics, that we actually need a dimension W that is higher than X, and that we can't, as it was done in previous work, restrict our dimension to the same dimension as the input system. So yeah, those are particular examples where you can see that you need these higher dimensions. And that it's an open problem, like how high you actually have to go in order to achieve the optimal value. And before I finish, I want to discuss one last thing we have in our work, which is a very related concept, which is the privacy funnel. So if you start from the information bottleneck, you get the privacy funnel by doing one easy step. You exchange the 2 mutual informations in their place. Now, this is called the privacy funnel. And you might be wondering, is that even like any meaningful thing to do? So there's a very intuitive explanation of why you might be interested in the quantity, which is now look again at like a correlated set of data, X and Y. Just call X some public data. So this is data you're willing to disclose to, let's say, a company who's supposed to do something for you, right? And this data, your public data, is also correlated with private data. This you want to keep secret. And now you have a channel from X to W again, which is telling you which data can you release. And the optimization in the privacy funnel now asks the question, can I minimize the correlation of my release data with my private data while maximizing the information it has about my public data? And this is something, I mean, clearly it's a very related concept, and it has some applications in classical information theory, but it does not have like an operational interpretation. And so we were trying to see if we can use our program we developed with information bottleneck to apply it also to the privacy funnel. And in the first step, this works very easily. So we can show that the classical and the quantum version of the privacy funnel are indeed convex. So this is the first good step and might be very useful for applications. But the second step, unfortunately, doesn't work as nicely. Does it have an operational interpretation? Already in the classical case, the answer is probably not. And the reason is the quantity turns out to be non-additive. So what does it mean? If PT is my privacy funnel function for a certain parameter t, then npnt is the same function applied to n copies of the state and then normalized by 1 over n. And optimally, if the function is additive, I would like to these two quantities to be the same. And this is important if I look at an operational interpretation in an information theoretic sense, because generally information theoretic means that I do something to n copies of a state towards a certain goal, and afterwards I want to let go n to infinity, and I would want to recover my single letter formula. And the fact that it's non-additive means that in general we can't do that. That doesn't mean there can't be an operational interpretation, but at least not in any of the straightforward ways which you usually use. So just a brief idea, how do we prove this? We can actually use the classical privacy implication protocol to show one particular point of the privacy funnel function in like this regularized case when we let n go to infinity. And using some other functions of the privacy funnel, like convexity, we can actually show that the regularized version with n to infinity has a very simple form, while we know actually that the single letter formula cannot have that form, like the function is not that simple if n is 1. Okay, so conclusion is we can't have any simple way of providing operational interpretation for this quantity. And I think that's actually all I wanted to talk about. So for more details, I refer to the long version of the paper. And thanks a lot for your attention.
Thanks, Christoph, for nice talk. Any questions? We have plenty of time.
Hi. Here. So you mentioned something about associated source coding, right? Mm-hmm. So is there a one-shot analog of it? Like if you can replace your bottleneck function by some epsilon smooth one-shot bottleneck function or something?
I mean, the task, you could clearly make like a one-shot function out of, a one-shot problem out of it.
Yeah. So if we can start off with one short instance of the problem and then take n copies of it and then generalize to get the asymptotic result.
Right. I mean, I suppose you could do that. You could go for like, for the information bottleneck, you could do that. You have, if you find like a one-shot solution to the problem, you take like the n copies limit and you should get it. I'm not sure if that would work for the privacy funnel too.
Okay, yeah, because I guess the smoothing will be an issue somewhere in doing the privacy constraint.
Yes. Okay. But for the information bottleneck, also just from information theoretic perspective, it would be interesting to have like a one-shot version of the assisted source coding problem.
Okay, thanks.
Any other question?
In your slide, you motivated your work investigation of information bottleneck using machine learning. and you studied quantum information bottleneck, and is there some application to machine learning, or this direction of study is there?
Yeah, so I mean, what I try to motivate is that this might be something we can look at a certain point, because I mean, now there have been many attempts in the past to define like quantum neural networks, for example, right? So one possible thing people might look at in the future is like to use the quantum information bottleneck in order to benchmark or to investigate the behavior of quantum neural networks. However, like some of the problems I mentioned, like the unbounded dimension of W, mean that in general, especially for like large data sets, it's very hard to currently optimize or find like numerical algorithms to calculate the quantum version of the information bottleneck. So there would, yeah, it would need some more research to figure that out. But then, yeah.
Thank you.
Any other questions? So if not, let's thank the speaker and all the speakers of the morning session.